ஹலோ. கேக்குதா? உங்களுக்கு கேக்குதா? கிளியரா கேக்குதா? ஹலோ. சரி, ரைட், ஓகே. இது இப்ப என் ஸ்லைடு இப்போ தெரியுதா? சரி, ஃபுல்லா தெரியுதா எப்படி? ஓகே, இது ஒரு நிமிஷம். ஃபுல் ஸ்கிரீன். இப்ப ஓகே, ஒரு நிமிஷம். இப்ப கரெக்டா இருக்கா? ஓகே. Extend my thanks to the convener and organizing secretary for giving me opportunity to participate in the faculty development program. Okay. So now, as in the faculty development program title, so today I would like to deliver a lecture on the clean energy system, clean energy. So what are the, it is not like a research detail. So I'll give how we can get a clean energy, and then what are the research gaps we are having. So those who are, you want to start up a research in the field of clean energy, it may be useful for you. So like that's some basic thing. And then related to this work, we published a review paper we are published in the last year. So from that only, I am going to give the details to you. Okay. So today's topic is we are going to give a lecture on the chalcogenide for the mid-temperature thermoelectric material. So thermoelectric material is nowadays a field growing very faster. So thermoelectric means we are converting the thermal energy into electrical energy. So thermal energy means from the waste energy we can able to produce the electrical energy. So that's a point we are having the thermoelectric. So for a simple example, we want to say now we have a Tesla car we are having. So the Tesla car, they are having the research on the thermoelectric material. So when you are driving a car, so when you are applying a brake, so the brake will produce a huge number of thermal energy. It will be produced. So it will be going to a waste one. So what they are doing now, so in the brake pad, they are making with the help of the thermoelectric material, and then that waste energy they are converting into the electrical energy, and that energy they are using for the charging the battery. Like that, they are having in the body like that. So many wherever waste heat we are having, so that heat we can convert into the electrical energy. So that is the main thing we are having in the thermoelectric material. So obviously in our India, how we are using a solar energy we are having. So most of the day we are having the heat, very good sunlight heat we are having. So that we can convert it into the electrical energy. So that only we are going to discuss. And then clean energy. So how we can define a clean energy now? So the clean energy is a power from the source that produce little or no greenhouse gases. For example, we have a carbon dioxide gas we are having. So that carbon dioxide gas or some other reaction, it will maybe produce. So that we can reduce. And then clean energy we can get from the solar energy, and then wind power, and then hydrothermal. These are all the things we are known popularly, but nowadays the thermoelectric material taking in that place. So in the solar energy, we know that it converting the sunlight into the electrical energy, and then wind energy, that also whereby turbining the blade we can get the electrical energy, and then hydropower, we are using the water pressure we are using to produce the electrical energy, and then geothermal we have. So from earth we have the heat, so inside the core we are having the heat, so that temperature we are using to produce the electrical energy, and then nuclear power, if you all you know. And then why we need a clean energy? So the clean energy will produce very less number of pollution or zero pollution, we can say. And then better health. So compared to the nuclear power, if you are taking now, when you are loading the material, we have some lifetime. But this clean energy, we are not having that lifetime. It will have more than 15 or 20 years we can get from the solar energy. And then endless supply. So renewable energy, we are having. Yes. Yes. Yes, Mas, sharing. Just a minute. Once again, I will see. So now, can you see? Oh, okay, right. Oh, okay. Okay, right, man. Okay. Right. Okay, so for this reason and all, the less pollution and then better health and then endless supply, we are using the clean energy we are using. And then, so the outline of the today presentation is we are going to see some introduction about the thermoelectric material, and then how the thermoelectric material is working, and then what are all the different methods we are having, and then how we can improve the power. For example, if you are taking a solar cell, we are taking for 20 years before, when we are working on the solar cell, the efficiency of the solar cell will be a 5% or 6%. Now, after a lot of research we made on that, and then now we are having efficiency of 25% efficiency we are having. So like that, in thermoelectric material, now we are having a 5 to 8% only we are having the efficiency rate. So we have more opportunity to work on the thermoelectric material, and we can enhance the efficiency. So that what all the different parameters we are having to enhance the power of the thermoelectric material, and then characterization. So what are the different type of what are the characterization we have to do for the thermoelectric material? So these are all the things we are going to see now. And then the introduction. So as we know that we are using the to produce the electrical energy, we are using the fuel source we are using. So one day the fuel it may not be get. So for that we need a immediate change in the producing the energy. And then global requirement also, we are having high requirement we have for the electrical. So nowadays, without electronic system or electrical energy, we cannot able to pass 1 hour. Like that we are practiced. So thermal energy is the electrical energy we need much more. And then, so for this, the thermoelectric material, we are having a promising solution for to meet our requirement without affecting our environment. So there is a concept of energy saving. And then why thermoelectric we need? So in the thermoelectric material, we don't need any moving part, or there is no chemical reactions will be there. So for example, if you are taking a nuclear power plant or thermal power plant, hydro power plant, like that, if you are taking there we are having some movement part will be there. So if you are having movement partner, we go for some maintenance work will be there. So the cost will be a very high. But in thermoelectric, we are not having like that. And then from this, the electrical energy directly it will be converted. So from heat directly it will be converted. And then we are using only the waste heat to recovery. And then in the space exploration, they are using the isotopes, radioisotope, thermo generators they are using. And then, as I told, in this thermoelectric material, what is the challenging we are having now? We are having efficiency of the thermoelectric material. We are having only 5 to 8% only as of now we are having. So this is not a challenging. We have more opportunity to work on this in order to enhance the efficiency of a thermoelectric material. So here, when we are talking about the thermoelectric material, so we are having the figure of merit is a very, very important point. So this figure of merit, when you are having a higher value, then your thermoelectric material having a high conversion efficiency will be there. So this figure of merit value is mainly depends on the 4 parameter. So one is the Seebeck coefficient, and then electrical conductivity of the material, thermal conductivity of the material, and then temperature. So the figure of merit, to identify that, we have a formula S square sigma T divided by K. So all the things we are having. And then related to the thermoelectric material, we have a 4 effect we are having. So all the 4 effect it can applicable for the thermoelectric material. So Seebeck effect, most of them we have know very well. So when we are having a 2 conductor at different temperatures, you are having then it will able to produce the electrical energy. So that's the voltage from a temperature gradient. 2 different temperature you are having a conductor, it will produce that. So that is called the Seebeck effect. Like that, we are having a Peltier effect. So in the Peltier effect, we are having a junction. For example, if you are having a 2 metals, you are having, so the 2 metal, we are made with the help of that, we are making a junction, like our PN junction diode. So when you are having a 2 metals, you are combining, when you are heating or cooling the material, we can able to produce the electrical energy. So that is a Peltier effect. And then Thomson effect is the material, like our thermoelectric material, it is not a single material. When you are changing the temperature of the material, it will produce the heat energy. Sorry, it will produce the electrical energy. So there's a 3 type of effects we are having. So this will be used in the thermoelectric material. And then thermoelectric material, when we are saying temperature, so based on the temperature, this thermoelectric material we can classify it into 3 categories. So one is the low temperature, so less than 300 degree. So your material working or having the thermoelectric characteristics less than 300 degree mean, then it is called as a low temperature thermoelectric material. And then mid temperature mean from 300 to 600 degree is called as a mid temperature thermoelectric material. And then high temperature we call it as a more than 600 degree. If your material having the thermoelectric nature, then it is called as a high temperature. So here people are mostly working on the mid temperature. So low temperature mean we have to limit the application. So conversion, we can go for a limited application we are having, but mid temperature from 300 to 600, we can go for the industrial, from industry like that you are having, you can convert the energy. So low temperature will be used in the home appliance and the car and all, we can use the low temperature material. And then high temperature material, we can go for the companies and all, the mid and the high temperature both. And then this topic we are going to give about detail about the only mid temperature. So what all the material we are used, and then how we are preparing. And then for that we have to choose the chalcogenide material for a mid temperature. So why we are choosing this chalcogenide material mean it is having a favorable electronic structure. So when you are having oxygen, sulfur, selenium and tellurium we are taking, so outermost we are having a 6 electrons we are having. So this structure is very, very important for to generate the thermoelectric material. So for example, some material we are given, so lead selenide, tin selenide, tin sulfate, indium selenide. So like that materials are having a good efficient for the thermoelectric applications. And then synthesis method. So in the synthesis method, we have a number of methods we are having, but most commonly we are using the one of the crystal growth method we are using is called the Bridgman and Stockenberg method. So if you want to make a crystal form, electronic thermoelectric device, you want to make in a form of crystal, we have to go for the Bridgman method. And then if you need for a thin film form, we have to go for the direct vapor deposition method. We have to go. And then if you need in a powder form, nanoparticle, like that, if you want, we can go for the rest of the method. So hydrothermal, solvothermal method, solid state reaction, and then melting, ball milling, and then mechanical alloying. So these are all will produce the nanoparticles. So in each category, we are given one example. So in the form of crystal, thin film, and then nanoparticles. So here, most all of you know, so how we are growing a crystal with the help of the Bridgman method. So in Bridgman method, we are having the crucible we are having. So in the crucible, we have to load our material. So what are the material you want to, we have to grow it, we have to fill it, and then we have to evacuate the system. And then from the top to bottom, we have to slowly, we have to drop the ampule. So in the ampule tip, we are having a narrow tip we are having. So when you are dropped in the top of the oven, upper oven, we are having a high temperature, and then the lower oven, we are having the lower temperature we are having. So when very gradually you are dropping the ampule from top to bottom, when the tip reaches the lower oven, from wet liquid to solid, the transformation will happen, and then we can able to get a crystal we can able to get. And then another one, we are having a hydrothermal and solvothermal method. So here we are using with the help of the high temperature with a high pressure, we are applying on the material. So for example, we are given this setup is called as autoclave. So in the autoclave, so what all the material you want to synthesis, that material we have to pull it. For example, if you want to grow a zinc oxide, you want to grow means we have to take a zinc chloride, we have to dissolve in water, and then we have to add the reactive agent NaOH. We have to add, and then we have to keep it in the oven. The Teflon coated thing we have to keep it, autoclave we have to keep, and then we have to cover with the bolt nut assembly they are given. With the help of that, tightly we have to close. Then this whole setup we have to maintain at a high temperature from 100 to 250 degree. When you are keeping at 100 degree, but is whatever we are taking a water, we are taken as a solvent. So the water will be evaporated at 100 degree. So inside the autoclave, a high pressure it will be produced. So in front of the high pressure and the high temperature, so the zinc react with the oxygen in the gaseous molecule, and then we will get the zinc oxide particle we can able to get. So here, what is the difference between hydrothermal and solvothermal? Is very simple. So hydrothermal means if you are using water as a solvent, if you are using then it is called as a hydrothermal. So instead of water solvent, if you are using some other solvent like acetone, ethanol, methanol, like that solvent you are using, then it is called as a solvothermal method. So depends on the remaining rest of the procedure are same. What type of solvent you are using, based on that we can classify the hydrothermal and then solvothermal method. And then solid state reaction. So this also we are taking a two component. For example, I am taking a two component. If I want a tin selenide, I need we can take the tin chloride and then selenium we can take, and then both we have to grinding together well, and then we have to keep it as a annealing at higher temperature, 1000 degree or 1100 degree if you are heating so the chlorine will be evaporated, and then the reaction will be taken place, zinc and selenium, and then finally we will get the product we will get. So if you want a bulk product, if you need we have to go for the solid state reaction method. And then ball milling. So the ball milling is a very famous technique to produce the nanomaterials. So here we are using a different size of balls we are using. So we will put it in a container. So this container we are going to rotate about an action. We have to rotate it. So while rotating, rolling it, like a planetary motion, we have to rotate it. So while moving it a planetary motion, the ball will roll inside the beaker. So because of that, the material will be crushed and make it as a nanoparticles. So it's a ball milling method. And then chemical vapor. So here it's one of the thin film deposition method we are having. So here we have to evaporate the material, and then with the help of the carrier gas, we have to transport to the thin film substrate and we have to deposit. For example, if I want to make a tin selenide, again, we want to take a tin selenide in a tin and selenium, we have to take it, and then we have to separately, we have to evaporate. After evaporation, with the help of the carrier gas, we have to send it to the surface of the substrate. Then the film will be starts to grow. And then, so these are all the most commonly methods we are using to get a thermoelectric materials. Okay, and then how to we have to enhance the efficiency. So as I previously told, we have a solar cell. By doping concentration or improving the crystalline structure, we can enhance the efficiency of the solar cell. So like that, what are all the different parameters we are having to enhance the thermoelectric material? So in that first thing, we are having the doping material. So here, while doping the material, we can enhance the Seebeck coefficient value, we can enhance. So Seebeck coefficient, already I told, that is mainly depends on the electrical conductivity and the thermal conductivity of the material. So by doping, we can alter the electrical conductivity, we can alter, as well as thermal conductivity also we can alter. So by choosing a proper doping material, we can easily alter the Seebeck coefficient value. So for example, we are given, so we are having a lead selenide, they are doped with the Na, sodium, and then they are having the Seebeck coefficient, they are having a 1.2 at 800 Kelvin. So like that, when you are using a different dopants, if you are using the Seebeck coefficient value, it may be changed. And then nanostructure. So we all of you know very well. So quantum confinement effect, we are knowing that. So when the particle size we are changing, the electrical property of the material also, it will change. So when there is a change in the particle size, there is a change in the electrical behavior. So that induce a change in Seebeck coefficient. Okay, so that we have a nanostructuring. We can control or we can improve the efficiency of the thermoelectric material. And then band engineering. So in order to alter the band gaps, we can able to control the Seebeck coefficient, we can control. And then defect. So defect, we know that. So if you are having a solid crystal or thin film, if you are having surely we are having some defects we are having. And then the thermoelectric material, it will working at a high temperature. So if you are having a defective place you are having, in that area, when you are applying some heat energy, obviously the defective area, element, atoms, whatever we are having, it will start to vibrate. So due to the vibration, it will produce the phonons, it will be produced. So that also will cause us the change in the thermoelectric material. That is a Seebeck effect value, it will be vary. So we have to minimize the defect. That's a concept we have here. So as we discussed here, so when by changing the doping, we can increase the Seebeck coefficient by optimizing the electrical and thermal conductivity. Similarly, nanostructure, we have a lead selenide and we can reduce the thermal conductivity. We can reduce. And then band gap engineering. So that we can increase the, while altering the band gap, we can increase the Seebeck as well as the conductivity of the material. And then in the defect, so the defect, if you are having a, we can reduce the thermal conductivity as well as the electrical conductivity, we can adjust to improve the Seebeck coefficient. And then, so how we can characterize? So we are saying that we are having the thermoelectric material. So after synthesis or preparing the material, whether the material it is having the thermoelectric characteristics or not. So for that, we have to go for characterization. So mostly in all the places we are having XRD, UV, like that we are having. So from the XRD, we can identify the what type of material or what type of unit cells we are having in the material that we can identify. And then planes, all the things we can identify. From UV, we can identify the optical behavior, like that dielectric we can identify. But for the thermoelectric characteristics, we are having a limited instruments only we are having to find the thermoelectric. So this is the to measure the Seebeck coefficient. This is the experimental arrangement we are having in order to find the thermoelectric characteristics of our material. So here we are having a heating furnace we are having. So in between the heating furnace, we are going to keep our sample we have to keep. And then in this, we have to apply the current. In the two end, we have to apply the current. So for that, we have to measure the temperature. In a different place, we have to measure the temperature as well as the current we have to measure. So at a different temperature, we can see we can get a volt current, how much it is varying with respect to this heating. So we have to gradually increase the temperature. By increasing the temperature, how in at a point T1 and T2, how the electrical behavior is changing, how much voltage is producing, that we can identify. So this is an experiment we are having. And then in order to find the electrical conductivity, we are having the 4-probe setup we are having. So in this 4-probe, we are applying the current. So from pin 1 and 4, we have to apply the current we have to apply. And then in between the two current, how much voltage is flowing, that we have to measure. So after measuring that, by applying the Ohm's law, we can easily identify what is the resistance of the material. So from that, we can able to identify the conductivity. Okay. So now what we are doing now, this same 4-probe method we are using to identify the thermoelectric material. That we are changing by changing the temperature. So what will happen? There is our applying current will be a constant one, and then voltage it will be vary. Like similar to our semiconducting material, the value will be changed. So from that also we can easily identify what is the whether our material having the thermoelectric characteristics or not. And then, so in the previous slide, this we are given, we are using a heating furnace we are using. And then nowadays, latest we are having the laser induced thermal conductivity measurement we are having. So instead of heater, they are using the high power laser they are using. So with the help of the laser, we can increase the temperature of the sample and finding the thermoelectric nature. And then in addition to that, we can employ the machine learning process we can employ in order to enhance the efficiency of the thermoelectric material. So already in the cloud, we are having the data will be available there. So from the data, we can come and conclude for what type of changes we can make to enhance the thermoelectric nature. And then scalability and cost consideration. So here, if in order to you want to go for the bulk material, if you want to go now, we have to spend more amount, and then more time it will be consumed. So we have to take care of the cost of the material also. And then sustainability and environmental benefits. So as in the introduction, I said
அவரோட பேஸ் வாய்ஸ் மட்டும் தான் வந்துச்சு. இப்பதான் வருது ஸ்கிரீன். Sustainability and environmental benefit.
So sustainability and environmental benefit. So here, tin chloride is a non-toxic material and it will be eco-friendly materials we are having. And then it will reduce the environmental degradation. So already we are using a polymer and plastic materials we are using. So for degrade, it will take a number of years it will take. So when we are using this kind of material, it will be reduce the contamination in the our air. And then applications. So as I told, in automotive, waste heat energy from car engine heat and then brake pad, like that heat we can convert into the electrical energy. And then industrial exhaust. So exhaust, it will we are having a more heat energy in the exhaust. So when the thermoelectric material you are applying on the exhaust or the exhaust pipe itself you are made with the help of the thermoelectric material, easily we can produce the heat energy from the waste. And then power generation from the waste steam also we can do. So all that things we have to make it as a device. And then device level integration. So now what we are doing now, the research is going on. So we are having already, we are having a solar panels we are having. So in the solar panel, what it will do, it will convert the light energy, sunlight energy into electrical energy. Okay. So there we are having the more heat energy we are having. So that heat energy we are not converting. So now what we are doing now, we are preparing the thermoelectric material and we are applied on the surface of the solar cell. The material, it should be a highly transparent material. So like that, we have to concentrate on that. So if your material is not having transparency, it will affect the efficiency of the solar cell also. So a high transparent thermoelectric material we are preparing and applying on the surface of the solar cell. So as usual, solar cell will produce the electrical energy. In addition to that, this thermoelectric material also will produce the heat energy. So like that, we are doing the research on that. And then for the thermoelectric material, what are all the material as on date we are using now? So lead telluride, 18% will give the contributing. And then bismuth telluride, it's a 19%. And then silicon germanium. So these three materials are most dominating material we are having the thermoelectric nature. And then emerging promoting materials. So solar cell, as I told, 20 to 40% we are having. We are taking energy from the solar cell. And then fuel cells, maximum we are going up to 60%. And then mid temperature, we are having only 10%. And then high temperature thermoelectric, we are get at 25%. So this is the efficiency of the different type of energy conversion. And then key design of principle of the high thermoelectric. So when you are planning to fabricate or you want to synthesize the thermoelectric material, we have to keep in mind all these points. So crystal symmetry, the crystal structure also very important to get the thermoelectric nature. And then what type of dopant we are using and the material whether we are going for doping or we are going for alloying. Based on that, the efficiency will be vary. And then structure, as we told, structure also make a role in the thermoelectric material. And future, this we can go for the atomic resolution. So we are going for the nanomaterials research we are going, so that we can take into the atomic level and we can characterize that and we can identify. And then we can apply the AML, artificial intelligence and machine learning, to get the accuracy of bore, what type of doping we can do, and what type of crystal structure we are having. We have high efficiency. Like that thing we can do. And then cross material mechanic learning. So this is a thing we are working on, the cross material. So we are having the thermoelectric material. So in that thermoelectric material, we are doping with the semiconducting material. So here in thermoelectric, what we are doing, we are converting the heat into electrical energy. In the same time, when you are taking a semiconductor, when you are increasing the temperature, the conductivity of semiconductor is increasing. So when you are adding a semiconducting material to the thermoelectric material, it will be giving a good efficiency. So that also we are working on that. And then while doing that, what are all the different challenges we are having? So if you are increasing the Seebeck coefficient, the conductivity, it should obviously it will go to the down. Thermal conductivity, sorry, electrical conductivity will go down. So if you are having Seebeck effect in your material, it can able to produce the electrical charge. Because of this lower electrical conductivity, the material will not get that much of efficiency. So to considering this point only, we are adding the semiconducting material. So semiconducting material, when you are adding, it will produce more free electrons, and then it can easily transport. And then lower thermal conductivity may reduce the mechanical strength. And the nanostructure introducing carriers or scattering, and then we are having the balancing effect, cost and stability. These are all the challenges we are having when we are working on the thermoelectric material. And then pathway to the sustainable energy. So next generation waste heat we have to consider more. We have to convert into electrical energy. And then, so what are the things we are discussed here? So to comprise all the thing, we are having more detail we are provided. So by year wise, we are given, and then material for each material, what are the different type of synthesis material they are chosen, like that. All the things we are given as a review work. So after this review work, we are having a good idea to work on the thermoelectric material. So if in this audience, any one of you want to work on the thermoelectric material, we have number of review papers we are having. So you can go through that, you will get a good idea. So why we are focusing on this thermoelectric material, the efficiency, we are having very less efficiency. So that we can do, we can enhance. So last 10 years before, if you are taking all the people, they will work on the solar cell, and then now they reach the maximum efficiency. After that, we are not able to enhance the efficiency. So we are moving for the another alternation method. So this will be a good field for another 10 to 15 years. It will be a very good work we can get from this method. Okay, and that's all from my side. From audience, if you want to ask any doubt, any clarification, you can ask. So one of the person there asked, sir, what about the antimony compounds? Antimony we can use, but it is a little bit unhealthy for our human body. So that we have to take care. Antimony while using, it's somewhat toxic. So we have to take care that also. Thank you. Thank you, all of you.